Hello dear students. So, today we will continue our discussions on atmospheric thermodynamics. Last class we have seen the basic gas laws, how we define what is the universal gas constant and how we calculate the mean molecular weight of the atmosphere, which is dry air. Then we have seen how the things change if you add some water vapor into it, right. So, in the last class we concluded our discussion on this equation, which is called as the hypsometric equation, which tells you what is the height separation between two layers of atmosphere which are existing at two different pressures, let us say. So, the pressures were identified to be P1 and P2. So, you have a layer of atmosphere which is separated by these two pressure surfaces. The height difference between them in, let us say, in the units of length is given by this equation. So, the equation can also be converted to find out what will be the pressure at any given point with respect to the pressure at the surface, right. So, we realized in these calculations we came across something called as the scale height. Scale height is the length dimension over which the pressure drops to 1 by e-th of its original value or the beginning value, right. So, scale height is generally written if you do not use the temperature, average temperature of a layer. So, generally temperature structure within this layer varies or decreases with respect to height. So, if you take an average temperature, that means if you take the picture to be isothermal in nature, you say that average temperature is this, so then you will get the scale height to be this. So, today we will continue our discussion and we will try to explore some ideas of the basic laws of thermodynamics, how we can write these basic laws of thermodynamics in terms of the variables which are relevant for our discussions ahead. Okay. So, in that way, so we will talk about specific heats first. So, what is specific heat? These fundamental aspects must be very well known to you already, right. So, for example, specific heat. So, suppose a small quantity of heat dq is added to a unit mass material, and as a consequence of adding this heat, adding this amount of energy to the system, to the material, if the temperature of the material changes from T to T plus dt Kelvin, let us say, without any change in the phase of the material. So, basically what you are doing is you are adding certain amount of heat to a system and you are expecting that this system does not allow or does not go under any phase transitions, and if this system's temperature increases from an initial value of capital T to T plus dt. So, the ratio of the heat supplied to the temperature change is called as the specific heat. So, the specific heat is defined in this way. I mean, if you define the specific heat in this way, it can have many values. So, what do you mean by many values? So, if you do not, of course, you have avoided the possibility of any phase transitions. So, that means that if you are talking about vapor, it will stay in the same phase like that. So, right. So, if you do not allow any phase transition to happen, but still if you define your specific heat to be just a ratio of heat to the temperature change, it can have any values, right, any number of values depending on how the material changes or how the material behaves as it receives the heat, right. So, if you keep a constant volume, then how does the temperature change? Because generally if you take a gas, if you add some heat, generally what will happen? The first thing that will happen is its internal energy will increase, and if the gas is not bound by a constant volume, its volume will change. That means the external heat that is supplied will cause the internal energy of the gas to change, and also some work being done by expanding the volume, right. So, this is the general first law of thermodynamics, right. So, in that case, if you do not define what is pressure change in this particular process, or what is the volume change in this particular process, then simply the ratio of heat supplied to the temperature change can have any number of values, right. So, it basically depends on how the material changes as it receives the heat, how the material's volume or pressure change when it receives the heat. Let us say, for example, if you confine the volume to be a constant, then the gas cannot do any work on the system, right. So, the gas cannot do any, the system cannot do any work. So, gas cannot expand. So, in that case work done is 0. That means, the entire energy that you have given to the gas will simply make the internal energy of the gas to go up, right. So, in that case whatever the temperature that you change, that you experience within the gas will be different. But if you allow a small possibility that volume can also change, then you are making the temperature change different from what the earlier case was, right. So, let us say if the material's volume is kept constant. So, rather than having many number of values, if you keep the material's volume a constant, the specific heat is defined at constant volume. The specific heat at constant volume is generally given by Cv. Specific heat at constant volume is Cv dq, the same ratio again, ratio of heat supplied to the temperature change, but at constant volume. However, if the volume of the material is kept constant, one very important consequence is that, so from the first law, dq is equals to du plus dw. du is the change in the internal energy, we will write it as it is, plus dw is p dv, right. So, if the volume is kept constant, this term dv becomes simply 0. That means that dq is just du as a consequence of this. So, you have defined Cv, or let us say C, the specific heat, as dq over dt. Now, your dq has now become du over dt, or du, the change in the internal energy, is Cv times dt. But for our discussion, we define the specific heat as the ratio of change in the internal energy as a function, as a result of the additional input of heat to the change in the temperature at the constant volume, right. So, Cv can as well be written in its own definition dq by dt, but since it is a process at constant volume, this is equivalent to this, right. So, from the first law of thermodynamics again, we know that dq is equals to du plus dw. Now, we have introduced alpha, which is the specific volume, right, volume per unit mass, right. So, du is now written as Cv dt, and dw is not p dv, rather it is p d alpha, right. Alpha is the specific volume. The internal energy U is a function of the state, right. Now, we have seen that internal energy capital U is a function of the state. That means, if you define internal energy for a particular system, it has to be defined at a particular state. Now, if this system changes from one state to another state, or if the system undergoes a change, then the change in the internal energy of the system will be just a difference between the final state minus the initial state, but it will not depend on the path through which this transition of state 1 to 2 has happened, right. So, it only depends on the initial state and the final state. So, this is what it is. I mean, the change in the internal energy U2 minus U1, in which the change in the internal energy is not dependent on the path, but only the final state 2 and the initial state 1. So, U2 minus E1. So, why is U2 minus E1 relevant here is that if you keep the volume of a gas constant and if you supply some heat, then the change in the temperature will depend on the change in the internal energy, but nothing else, because du is equals to Cv dt, right. So, change in internal energy is from T1 to T2. So, the initial state and the final state characterized by temperatures T1 and T2, Cv dt. So, you can also write it like this, right. So, similarly, we can also define specific heat at a constant pressure. So, we have defined specific heat at a constant volume. So, at the constant volume, what is happening is you are giving heat. So, the molecules or the atoms are vibrating faster. So, they build up more pressure. So, whatever the heat that you have given is accounted in the sense that it is able to increase the pressure, right. But if you keep the pressure constant, if you don't allow the pressure to go up or down because of the additional heat that is being supplied, what happens? Then naturally you would expect that the gas will expand, then there will be a certainly change in the volume, right. So, the specific heat can also be defined at a constant pressure rather than at a constant volume. So, this specific heat is generally generally given by Cp. Cp is equals to dq by dt over at a constant pressure. So, here the material is allowed to expand as the heat is added to the system and its temperature rises, but its pressure remains a constant. So, you have a gas chamber. Previously, you kept the volume of the gas chamber a constant. Now, you allow a possibility that volume may change by dV when you supply an additional heat of dq. So, here how is the pressure constant? I mean, pressure is force per unit area. The average amount of force that is exerted by the molecules per unit area is the pressure, right. Now, if it is the case, then you are not allowing molecules to exert more force on the surface. That means, the molecules are expanding into the additional volume, right. So, most importantly, the material will have to be expanded to do the work. So, basically when dV is non-zero, it simply turns out that dW becomes non-zero. The work done is 0. The work done is non-zero. So, dQ is now du, of course, change in the internal energy plus dW. So, earlier case dW was 0, dW in this case is not 0, right. So, the material will have to be expanded to do the work as the system expands against a constant pressure environment, right. So, this is the most important thing when you discuss the specific heat and when you want to understand why do the specific heats differ by the magnitude of the gas constant. We will get there, right. So, the gas should expand such that the pressure is maintained constant. Generally, when you expand, what happens to the pressure? So, we know that PV is equals to constant, right. So, we know very well that PV is equals to constant. That means, if you increase the pressure, the volume will decrease. Simple, right. Simple to understand, even to comprehend, because if you put the same amount of gas in a larger volume, the force that is going to be experienced per unit area will obviously decrease. Less number of molecules will be encountered within a unit surface area. So, the force will be lesser, the area is still the same. So, that means that the pressure will be smaller, right. But if you want to expand the gas, but still keep the pressure constant, that means the energy that you are supplying is not only causing the gas to expand, but also a part of the energy is also utilized to increase the mean molecular velocity of the molecule, so that it exerts more pressure or equal pressure despite the volume changing, right. So, hence we need a larger amount of heat to be given for the material to expect a given change in the temperature, right. So, in the specific heat at a constant volume, what we have seen is that when we supply external heat into the system, the gas is not allowed to expand, the volume is held constant. So, for whatever the heat that you are supplying is simply transferred to increase the internal energy du, and you have defined your specific heat such that the change in the internal energy to the change in the temperature is the specific heat. So, that means whatever the amount of heat is given is directly being used to get a required change in the temperature. But here a certain amount of heat is already utilized for the change in the volume just to expand. Why should this be non-zero? Why should this change in the volume is not non-zero? Because you have not kept the volume to be a constant. Whenever you heat a gas, it is a natural tendency of the gas to expand and occupy more volume. If it is occupying more volume, it is natural to expect that it will exert lesser pressure over the enclosure. But if you still want the same pressure to be maintained, you will have to supply more amount of heat, as simple as that, right. So, hence a larger quantity of heat must be added to the material to rise its temperature by a given amount, by a given magnitude, by a given let us say by 1 Kelvin than what you supplied at constant volume. So, this is the basic reason why specific heats differ. Specific heat at constant pressure is always larger than the specific heat at constant volume. So, this is the basic difference. The only simply put, it comes because the effort to maintain the same pressure despite the change in the volume, right. So, for the case of an ideal gas, the difference between the specific heats is always, I mean, we use this particular quantity so many times in our calculations, right. So, for the case of ideal gas, the difference between the specific heats can be simply calculated. So, dq is equals to Cv dt plus, so this is, so you write dq as du plus dw, right, or dq is because at the constant volume du is Cv dt plus, so dq is du plus dw, du is Cv dt plus alpha dp, right. So, if you just rearrange this, you will have, so this is a derivative making sure, so d alpha p is alpha dp plus p d alpha. So, if you put this here, so this alpha dp gets cancelled. So, you still have dq is equals to Cv dt plus p d alpha, right. But we know that from the ideal gas law, P alpha is equals to RT, right. So, d of P alpha is simply R is a constant, so R times dt. So, dq is equals to, so we substitute d of P alpha as R dt. So, we take, I will simply write between the steps, dq is Cv dt plus d of P alpha minus alpha dp. I am not expanding this derivative and cancelling out. I am making use of d of P alpha is R times dt. So, dq is Cv dt plus R dt minus alpha dp. So, as a result I can write dq is Cv plus R times dt minus alpha dp, right. So, the point is Cv plus R, Cv plus R dq is nothing but Cp dt minus alpha dp, right. So, this is the transition Cv plus R. So, Cv plus R is Cp, or Cp minus Cv is equals to R. What is R? The gas constant, right. So, specific heat at constant volume and at constant pressure for dry air are 717 joule per Kelvin heat energy per change in the temperature. And so, specific heat at constant volume, so this is smaller as we have seen just now, Cv, and this is Cp. Unsurprisingly, as we know, Cp minus Cv, the difference between the specific heats at constant pressure and constant volume is 287 joule per Kelvin per kg. That means, if you want to rise the temperature of 1 kg of, let us say, a substance by 1 degree Kelvin, you will have to supply 287 joules of energy, right. So, which is equal to the gas constant of dry air, capital R. So, we know the values of specific heats and at constant volume and constant pressures. If you take an ideal monatomic gas like oxygen, O, the ratio of specific heat Cp, Cv and R are 5:3:2, and the ratio of Cp to Cv to R for an ideal diatomic gas will be 7:5:2. So, these numbers are very important that you remember these numbers. So, you will use these numbers many times in numericals and various exercises. Okay. Right. So, that was something about the specific heats. Why do you have to define specific heats is that when you discuss atmospheric thermodynamics, or when you discuss the path or the movement of an air parcel, you will have to understand why does heat gets emitted or why does heat gets absorbed. So, all these things, the physical processes that result as a result of exchange of heat will involve the understanding of specific heats, right. So, once that is done, we talk about what is called as enthalpy. Enthalpy is generally given in our earlier classes as the total heat content of a system, or let us say a gas. So, if the heat is added, let us say, so fundamentally what is enthalpy? If the heat is added to a material at a constant pressure, so that the specific volume alpha increases from alpha 1 to alpha 2. The work done by a unit mass of material then is P times alpha 2 minus alpha 1. So, what is being done is at a constant pressure, just like Cp, if we add heat such that its specific volume increases from alpha 1 to alpha 2. The work done by this effort by a unit mass of material is then P times alpha 2 minus alpha 1. So, now you have added heat and the volume has changed from one value to another value. So, if you write, so from the first law of thermodynamics, we always know that any amount of heat that is given to the system will first increase the internal energy of the system and will also do some work, right. So, since the volume change is non-zero, the work done is also non-zero, right. So, the heat that is given is delta Q can be written as the change in the internal energy U2 minus U1 and plus the change or the amount of work done. So, if you rearrange this equation, delta Q is U2 plus P alpha 2 plus U minus U1 plus P alpha 1. So, if here U2 and U1 are the final and the initial internal energies of the system. So, this is kind of swapped anyway, right. So, for a unit mass of material, if you say all this U plus P alpha 2 can be said as H2 and U1 plus P alpha 1 can be said as H2 and H1, right. So, for a unit mass of material at a constant pressure, we say that the heat given to the system is just equal to the final enthalpy state of the system minus the initial enthalpy state of the system. So, then we define enthalpy as the total heat content of the system. So, in the equation above, H is equivalent to U plus P alpha. So, now we know it very well that the internal energy, pressure and the specific volume are functions of state. So, functions of state means the change does not depend on the path that has been taken between the states. Rather, the change will only depend on the initial and the final configurations, right. So, because H is now equivalent to internal energy plus pressure times the specific volume, alpha is the specific volume, right. Because U, P and alpha are the functions of the state, enthalpy H is a function of state. So, if we simply differentiate the equation above is this equation, H is equals to U plus P alpha. If you differentiate this, dH is equals to du plus d of P alpha. So, dq is dH minus alpha dP. So, you have to bring in the specific heat equation. So, you can write the heat that is supplied. So, dq is du plus P d alpha and dH is du plus d of P alpha. So, du is equals to dH minus P d alpha minus alpha dP, right. So, this is du. We know dH. So, if you substitute this into this, you will get dq is equals to dH. Yeah. So, if you substitute du, I mean this equation goes into this part. So, dq is equals to dH minus alpha dp. Right. So, here, so then we say that dq is equals to Cp dt minus alpha dp. So, dq is equals to dq is now equivalent to dH minus alpha dp. So, h is equals to Cpt. So, h is now Cpt and du is now equals to Cv dt. So, these two are very important thermodynamical relations. So, we can write a more general expression by bringing the geopotential into picture. Right. So, what is enthalpy? Enthalpy is just a state function which depends on the internal energy, the pressure and the specific volume, right. Enthalpy depends on all these quantities. If you rewrite this equation, if you just substitute the first law of thermodynamics, we can realize that the enthalpy is equals to Cp times T, the temperature, right. So, if we remember our last discussion, we have seen what is the idea of geopotential, there is the work done, right. So, geopotential was defined as d phi is equals to g dz, which is also equal to from the hydrostatic equation. We also know that g dz is equals to alpha dp. So, dq is equals to dH minus alpha dp, that is the equation that we had, and h is equals to Cpt. So, if we substitute this into this equation, right. So, by combining these three equations, we can write dq is equals to d of h plus phi or d of Cpt plus phi. So, h is Cpt, this is being substituted here. So, Cpt plus phi. So, if the material is a parcel of air with a fixed mass, if the mass is not changing, is moving in a hydrostatic. So, hydrostatic equilibrium has allowed us to write this. So, dp by dz is equals to minus alpha dp. dp by dz is equals to minus rho g, yeah. So, hence if the material is not is conserved, the quantity h plus phi. So, this quantity h enthalpy plus the geopotential is generally referred to what is called as the dry static energy. This is called as the dry static energy. So, this is a constant provided the parcel neither gains or loses heat, right. So, this is how you bring in enthalpy to write the geopotential, and you define a physical quantity which is called as the dry static energy, and this dry static energy remains conserved if the air parcel is in a picture in which it is neither gaining energy or losing energy, right. So, I will conclude this class here. So, what we have learnt is we have learnt few details about specific heats, what is the reason for them to differ by the gas constant, and what is enthalpy, and how we can manipulate or rewrite several different forms of the first law of thermodynamics to write specific heat or to write enthalpy or to define what is called as the dry static energy, right. So, this is where I will stop. We will continue the discussion in the next lecture.